Okay, this is moment of inertia example number 5. And we're asked to determine the moments of inertia for the shape that's shown here. And I'm going to start off by doing it about the horizontal axis first. We're given that the centroid is located 5.538 inches from the left edge and 6.615 inches from the bottom edge. Okay, so the first thing I'm going to do is I'm going to break this compound shape up into a couple of primitives. I'm going to break it up into a triangle and a rectangle. And so this is going to be the triangle here. I'm going to call it subsection number 1 or subshape number 1. This is a rectangle down here. I'm going to call it shape number 2. Now each one of these primitives has a centroid. So there's the centroid of the triangle approximately. 1/3 of the base and 1/3 of the height measured from the fat end. We'll call that the x1 axis, and then the rectangle, if we find the lines of symmetry, it's going to be about there, and we'll call that the x2 axis. Now, similarly, this is going to be the axis that passes through the centroid of the compound shape, the major x-axis. And what I'm looking for is I sub big X. So what I'm going to do is go back to my equation sheet, and I'm going to look up the equations that I have for the moments of inertia for the primitives. And I'll start with the triangle first. And the moment of inertia of a triangle about its centroidal axis is bh cubed over 36. So what I'm going to do is I'm going to write that I sub x1 is equal to the base of the triangle times the height of the triangle cubed divided by 36. So that works out to be 12 inches for the base times the height is 6 inches. That's cubed divided by 36. And the math works out to give us a value of 72 inches fourth. Now I'm going to next calculate the moment of inertia of the rectangle about its centroidal axis. So let me go back to my equation sheet, and I can see that for the rectangle, the moment of inertia of that rectangle about its own centroid is bh cubed over 12. So let's see, I can write that I sub x2, that's a lowercase x, is equal to bh cubed divided by 12. So the base of the rectangle is 12 inches. The height of the rectangle is 10 inches cubed over 12 like that. And that gets me to 1,000 inches to the fourth. Now I can't add those two numbers together directly. I can only add moments of inertia together if the moments of inertia are taken about the same axis. So what I need to do is I need to convert the moment of inertia I sub little x1 to the moment of inertia of I sub big X for area 1. So that's the moment of inertia of the sub area 1, the triangle, about the big X axis. And this is going to be equal to the moment of inertia I sub little x1 plus A times D squared. We'll call that D1, we'll call that A1. And the distance D1 is this distance right here. The distance between the two axes that I'm converting. So let's see if I base like that. And I moved the other stuff too, I guess. That wasn't exactly. All right, let's see. Okay, now I got a little bit more space. I can go in here and I can say that this is equal to 72 inches to the fourth plus the area, 1/2 the base times the height of the triangle. So 1/2 the base, 1/2 the 12 times the height is 6 inches, and then times the distance d squared. So that distance is going to be 12 inches. So we go up 10 plus 1/3 of 6 is 2. And then we subtract out the location of the centroid of the composite shape like that, and then that gets squared. And when we push those numbers through, we end up with 1,116 inches to the fourth. Now do the same thing for the second area. So the moment of inertia of sub-area 2 about the big x-axis is equal to moment of inertia of sub-area 2 about its own x-axis plus AD squared. So this is going to be I sub little x2 plus A2 D2 squared. and the distance d2 is going to be, let's see, I'll illustrate it here, is going to be that distance. So here we have the local moment of inertia, 1,000 inches fourth, plus the area, which is just the base into the height, and then times the distance d. This is going to be 10 inches over 2 minus 6.615. That gets squared, and this works out to be 1,313 inches to the fourth. So now what we can do is we can add this number and this number together, and we can get the final answer. We can say that I sub big X for the whole shape is equal to 1,116 inches fourth plus 1,313 inches fourth, or it's equal to 2,429 inches to the fourth. All right, thank you. Okay, now we're going to take a look at the same example, except we're going to solve for the moments of inertia about a vertical axis. So let me go ahead and erase some of this stuff that I sketched in there. Let's see, I'm going to move that. So that's going to be sub-area 1 there. So these centroids are still valid. We won't need that. We won't need that. Okay, good. Now, this is going to be the little y1 axis. So that's y1 going through there. And this is going to be y2 going through there like that. So what I want to do now is I want to figure out what the moment of inertia is about this big y-axis here. So I want to know what I sub y is. So what I'm going to do is I'm going to go to my equation sheet, and I'm going to look up the moment of inertia for the triangle, and it's about the x-axis is bh cubed over 36. So about the y-axis it would be b cubed h over 36. So let me get rid of that, and I could say that I sub little y1 is equal to b cubed h over 36, and that's going to be equal to 12 cubed times 6 over 36 like that, which is equal to 288 inches to the fourth. All right, now I'll just work in order now. So if I want to know the moment of inertia about the big y-axis from sub-area number 2, this is going to be equal to that plus a times d squared. So this is going to be 288 inches to the fourth plus the area, 1/2 base times the height, and then times the distance. Now the distance that I'm looking at in this case is going to be this distance right here. So that is the distance d1. So that distance is going to be 12 over 3. And then I subtract out the value of x bar for the composite shape, 5.538 inches. That gets squared. And if we add all of that up, we get 373.2 inches to the fourth. Now for the second sub area, whoops, that's a mistake. That should actually be, sorry, sub area 1 like that. There we go. Okay. I sub y2 is equal to, let's see, if we go over here for our rectangle, I sub y is b cubed h over 12. Okay, let's get back to that. So this is equal to b cubed h over 12. So the base is 12 cubed, height is 10 divided by 12, and that's equal to 1,440 inches fourth. Now I sub big Y 2 is equal to that, 1440 inches to the fourth, plus the area, so 12 inches by 10 inches, times the distance, d squared, and this time it's this distance here, so that is d2, the distance between the y2 axis and the major y-axis. So that's going to be, see, 12 inches over 2 minus 5.538. Square that, and that number works out to be 1466 inches to the fourth. And now I can add those two numbers together, and I get a value of 1,839 inches to the fourth. So there you have it, the moments of inertia about the major x-axis and the major y-axis.